Hello, and welcome to G Fun Facts Online. For centuries, Mars has been the red planet in our minds, a dusty, rusty, and seemingly dead world. But what if I told you that beneath that desolate surface lies the ghost of a world once teeming with water? We're not just talking about a few puddles or ancient lakes. We're talking about a colossal river network, stretching an incredible 15,000 kilometers across the planet. Today, we're unveiling this spectacular discovery, a story etched in stone that is completely rewriting the history of ancient Mars. To really grasp the scale of this new finding, we need to rewind the clock on our own exploration of Mars. The idea of water on Mars isn't entirely new, but our understanding has evolved dramatically. It all started in the early 1970s. After waiting patiently for a planet-wide dust storm to clear, NASA's Mariner 9 orbiter sent back images that were truly revolutionary. For the first time, we saw features that looked unmistakably like dried-up riverbeds and immense canyons, including the now famous Valles Marineris. It was the first hard evidence that liquid had once carved its way across the Martian landscape. Just a few years later, the Viking program solidified this new picture. The Viking orbiters saw even more detail, vast outflow channels suggesting unimaginably huge, cataclysmic floods had burst from underground. They also spotted branched valley networks, especially in the southern highlands, which were a smoking gun for something even more profound: rainfall. It wasn't just floods, it seemed Mars had a water cycle. Meanwhile, down on the surface, the Viking landers scooped up Martian soil and confirmed that yes, water was a component, and the soil chemistry was exactly what you'd expect if it had been soaked in water in the distant past. From there, the evidence just kept piling up. In the late 90s and early 2000s, the Mars Global Surveyor gave us even higher resolution maps, revealing what looked like ancient lakebeds and gullies that hinted at more recent water flows. Then came the rock stars of Martian exploration, the rovers Spirit and Opportunity. These tireless, robotic geologists didn't just look at the landscape. They analyzed the rocks themselves. They found definitive mineralogical proof of past water, discovering rocks that had clearly been formed in or altered by it. Their findings led scientists to declare that Mars, at some point, must have been drenched. And the story continues with the Curiosity rover, which has been exploring Gale craters since 2012. Curiosity has found layered, sedimentary rocks that paint a vivid picture of what were once habitable rivers and lakes, further cementing the idea that liquid water wasn't just a brief visitor, but a persistent feature of the early Martian environment. So we knew there was water, we knew there were rivers and lakes, but the scale remained a question. That is, until the recent discovery in a region called Noachi's Terra. This finding has provided a whole new dimension to our understanding. Led by PhD student Adam Looskoot of the Open University, a research team uncovered a river network of truly epic proportions, 15,000 kilometers long. To put that in perspective, that's roughly the distance from New York City to Sydney, Australia. This wasn't just one river. It was an intricate, sprawling system of fossilized rivers. What makes this discovery even more remarkable is where it was found. Noachi's Terra is a vast, ancient highland in the southern hemisphere of Mars. It's one of the oldest surfaces on the planet. But historically, it wasn't the top spot for scientists looking for rivers. Why? Because it lacks the obvious, deeply carved canyons that scream river valley. So Looskoot and his team had to look for something far more subtle, a different kind of geological clue: fluvial sinuous ridges, also known as inverted channels. So what exactly is a fluvial sinuous ridge? It's a fascinating trick of geology where a river is preserved in reverse. Imagine a river meandering across the Martian plains about 3.7 billion years ago. Like any river, it carries sand, gravel, and silt. As the water flows, these heavier materials, the sediments, settle and get deposited on the riverbed. Over immense spans of time, groundwater can percolate through these sediments, carrying dissolved minerals that act like cement, gluing the sand and gravel together into a hard, durable rock. The surrounding floodplain, however, is made of much softer, finer-grained material like dust and silt. Now fast forward. The Martian climate changes dramatically. The atmosphere thins, the planet cools, and the rivers dry up for good. Wind becomes the primary force shaping the landscape. Over millions of years, the relentless Martian winds act like a giant sand blaster, stripping away the soft, loose material of the floodplain. But the cemented, rock-hard riverbed resists this erosion. The result? The softer ground is blown away, leaving the ancient, winding path of the river standing high and proud as a raised ridge. We're literally looking at the ghost of a river, preserved in stone, standing tens of meters above the surrounding terrain. It's a river in reverse. And these features aren't just a Martian oddity. We find them right here on Earth, in places like central Utah. This is fantastic for scientists, because it provides a direct comparison. By studying these terrestrial inverted channels, we can learn how they form and what they tell us about the rivers that created them. We can then apply that knowledge to Mars to infer things like the size of the ancient Martian rivers and how they migrated across the landscape over time. Mapping these subtle ridges across a whole planet is an incredible feat of what's called Martian paleohydrology, the study of ancient water systems on Mars. This science relies almost entirely on data from our robotic eyes in the sky, especially NASA's Mars Reconnaissance Orbiter, or MRO. Operational since 2006, MRO is a masterpiece of engineering. For the NOAA's Terra study, the researchers used a trio of its key instruments. First, the context camera, or CTX. Think of this as the wide-angle lens. It takes broad images of the surface, helping scientists understand the bigger picture and the overall geological context of a region. It's how they spot potential areas of interest. Next, they zoom in with the High-Resolution Imaging Science Experiment, or HiRISE. This is the most powerful camera ever sent to another planet. Its images are so detailed it could spot a rover on the surface from orbit. HiRISE allows for a microscopic examination of the ridges, revealing their texture, shape, and structure, confirming that they were indeed formed by flowing water. Finally, to understand the reverse part of these rivers, you need to know the topography. For that, they used data from the Mars Orbiter Laser Altimeter, or MOLA, which flew on the earlier Mars Global Surveyor. MOLA shot laser beams at the surface and measured the time it took for them to bounce back, creating incredibly precise 3D elevation maps of the entire planet. By combining the wide-angle CTX images, the detailed HiRISE close-ups, and the MOLA topographical maps, scientists can trace these ancient river systems, even when they are subtle, and prove that they are, in fact, ridges standing above the plains. This discovery of such an extensive, interconnected river network has thrown a massive amount of weight behind one side of a long-standing scientific debate about Mars' ancient climate. For decades, scientists have been split between two competing models. On one side, you have the cold and icy model. This theory suggests that early Mars was generally frigid and dry, much like it is today, with most of its water locked up as ice and permafrost. In this scenario, liquid water would have been a rare and violent event. Perhaps a massive asteroid impact, or a colossal volcanic eruption, would melt huge amounts of ice all at once, creating catastrophic, short-lived megafloods that would carve the landscape and then quickly freeze again. On the other side is the warm and wet model. This hypothesis proposes that early Mars was a very different world. It had a much thicker atmosphere, a stronger greenhouse effect, and a warmer climate. This would have allowed liquid water to be stable on the surface for long geological periods. It would have supported a full-blown hydrological cycle, just like on Earth, with evaporation, clouds, rainfall, and persistently flowing rivers. The evidence from Noachi's Terra is a huge point for the warm and wet team. The sheer scale, 15,000 kilometers, is hard to explain with just a few random floods. The rivers are interconnected, forming a true network, which suggests a widespread, stable source of water, like rainfall over a large area. The fact that some of these ridges are tens of meters high tells us the rivers that formed them must have been active for a very, very long time, steadily depositing layer upon layer of sediment. This isn't the signature of a brief, violent flood. It's the signature of a sustained, long-lived river system, which points to a much more stable and hospitable climate on early Mars than the cold and icy model would suggest. And this brings us to the ultimate question, the one that drives so much of our fascination with Mars. Could it have ever harbored life? The presence of long-lived, stable, flowing water is the single most important factor in that equation. Every form of life we know of requires liquid water to exist. On Earth, river corridors are biological hotspots. They are oases of life. They don't just provide water. Their currents gather and concentrate nutrients and organic molecules, creating rich, fertile environments. The rivers of Noachi's Terra would have created precisely these kinds of habitable environments on ancient Mars. If life ever did get a foothold on the red planet, the muddy banks and sandy beds of these ancient rivers would be the prime real estate. This is exactly why NASA's Perseverance rover is currently doing its work in Jezero Crater. Scientists believe Jezero was once a deep lake, fed by a river that formed a large delta. Perseverance is drilling into the sedimentary rocks of that ancient river delta, collecting samples that will, hopefully, be returned to Earth by a future mission. In labs here on Earth, we can analyze those samples with a level of precision impossible on Mars, searching for chemical fossils or biosignatures that could be the definitive proof of past microbial life. The discovery of the massive river network in Noachi's Terra dramatically expands the map of potential places to search. It suggests that these habitable, river-fed environments weren't just confined to a few lucky craters. They may have been widespread across the ancient southern highlands, making the prospects for finding evidence of past life on Mars even more tantalizing. So the mapping of this 15,000-kilometer river network in Noachi's Terra is more than just a new entry in a textbook. It's a landmark moment in our exploration of our celestial neighbor. It transforms our view of the red planet from a world of catastrophic, isolated floods to one with a more stable, persistent, and potentially life-sustaining water cycle. The winding stone ridges that crisscross the Martian highlands are silent storytellers, the fossilized remnants of a time when Mars was a much more dynamic and vibrant world, a world with blue rivers under a thicker sky. The story of water on Mars is still being written. With every new image from orbit and every rock analyzed by a rover, we add another page to the epic tale. We are peeling back the layers of a planet that was once very different, and with each layer, we get closer to understanding its history, and perhaps closer to answering one of the most profound questions humanity has ever asked. Are we alone in the universe? The ghosts of the rivers of Mars suggest that the answer might be more complex than we ever imagined. Thanks for listening to G Fun Facts Online.